is CORDIScovery. Hello and welcome to this episode of CORDIScovery with me, Abigail Acton. The best way to understand what's coming is to look at what has happened in a similar context in the past. So what can prehistoric ice tell us about sea level rise, one of the most damaging impacts of climate change, threatening the economy, the ecology, and the existence of coastal regions worldwide? Global mean sea level has risen by around 8 centimetres since 1992. Land ice loss and ocean thermal expansion contribute equally. The future of sea level rise is set to become dominated by the highly uncertain behaviour of the Antarctic and Greenland ice sheets. The potential for the rapid collapse of these sheets, which may already be underway, is making us aware of humanity's vulnerability to ice sheet change. So knowing how they are reacting to global warming is central to getting a clearer idea of what lies ahead. Our three guests, all of whom have received support from the EU's research and innovation funding, have been working on improving our understanding of these interactions. Here to share their work with us today are Eric Wolff, an honorary fellow of the British Antarctic Survey, who studies past climate and environment, mainly from polar, Antarctic and Greenland ice cores. He is a Royal Society Fellow Research Professor in the Department of Earth Sciences at Cambridge University. Hello, Eric.
Hello there.
Alessio Rovere, a professor at the Department of Environmental Sciences, Informatics and Statistics at Ca'Foscari, the University of Venice, is interested in paleoclimate and sea level changes and how geological processes have changed coastlines over deep time. Hello, Alessio.
Good morning, everyone.
Good morning. A director of research at the French National Centre for Scientific Research, CNRS, Gaël Durand, specialises in the modelling of polar ice sheets and the dynamics of coastal glaciers, with a focus on their impact on sea level rise. He's particularly interested in understanding the stability of ice sheets and their potential responses to climate change. Hello, Gaël.
Hello, thank you.
Eric, I'm going to turn to you first. The Waxwain project aimed to understand what happened to the West Antarctic ice sheet during the last interglacial period. Eric, when was the last interglacial period and why is understanding that important for us now?
So the last interglacial period is a few thousand years, around 125,000 years ago. And it's a period when we know that the polar regions were a little bit warmer than today. And there's evidence particularly from corals, suggesting that sea level was higher than it is today. So that suggested that the Antarctic ice sheet must have been partly lost during the last interglacial, and we're particularly interested in West Antarctica, which is considered the most vulnerable part. And as a glaciologist, it was kind of shocking to me that we didn't actually know. We didn't actually have any direct evidence as to whether the West Antarctic ice sheet was there or was completely missing at this crucial time in the past.
Gosh, yes, that's quite a gap in the knowledge, isn't it?
It is. So we tried to think of ways to find this out. And the approach that I took, because it's my speciality, is to drill an ice core in an area very near to the West Antarctic ice sheet, but that would be sensitive to the presence or absence of that ice.
Right. Okay. So that must have presented enormous challenges. Can you tell us a little bit more about how you go about actually extracting ice cores that are that old? I mean, there must be vast, great big long cores.
Yes. So this ice core was 650 meters long, but I don't want people to think
huge.
I don't want people to think that somewhere we've got 650 meters in one piece. It comes up in 1 or 2 meter sections and is stored in a deep freeze somewhere around Cambridge. So to do that, we had to go to the Antarctic. Well, firstly, we had to find the right place where we thought we would get this ice that was particularly sensitive to the ice sheet presence, and that was accessible to us. But it's a pretty inaccessible place. So I went in we did this in one field season. So a field season means about 3 months between November and January in the southern hemisphere summer. So we went in November 2018. We're a team of 8 people. Basically spent a lot of time digging, eventually drilling, cutting up ice with a bandsaw and putting it in polystyrene boxes in order to send them back to the United Kingdom for analysis.
Very carefully labelled polystyrene boxes.
All carefully labelled, and every core, actually, that's the one important thing. Every core has an arrow on it pointing up because it's a shame to turn 100 years upside down.
Oh, yes, that's true. I hadn't even thought of that. Thought of the labelling, but I hadn't thought of being up or down. Absolutely, indeed. And were you satisfied with the amount of samples that you managed to get? Did you feel that you were in the right place and that you got what you needed?
Yeah, so the crucial thing is we got to the bottom without losing the drill, which is always an important thing. So we've got 650 metres of core, and it turned out subsequently when we did the analyses that it does indeed go back to this period we were interested in 125,000 years ago. So after a lot of cold feet and cold hands, we had what we were after.
Okay, great. And how did you know by looking at it that what characteristics were you looking for that would indicate how old it was and that it was an appropriate sample?
Well, there are lots of ways to find out how old the ice is. We can actually match up with previous cores in other parts of Antarctica that have gone back to the same period, and certain things like the concentration of greenhouse gases, for example, should be the same in every ice core you drill in Antarctica, so we can match up the pattern. We also sent some samples off to a laboratory that can measure a radioactive element that's krypton 81 that's sensitive to the age of the ice. So we did some checks near the bottom to make sure we really did have ice the age that we thought we had.
Great. Okay. And what did the samples tell us?
So the most important two things that the samples told us. Firstly, it turned out that the ice is a little warmer than one would expect for that period, which actually implies that the ice sheet is thinner than it used to be, which implies that there was less ice in the past. So the West Antarctic ice sheet did partly disappear at that time. But then also it sits next to what we call an ice shelf, which is hundreds of kilometers of floating ice that have come off the ice sheet and sit over the ocean. And many ice sheet models suggest that under a warming situation, that ice shelf would disappear. We can tell whether that happened because we can measure sea salt in the ice. And sea salt, of course, comes from the edge of the ice, from the ocean water on the edge of the ice. So currently, the seawater is 600 kilometers away from where we were drilling. If the ice shelf had disappeared, it would be 50 kilometers away. So we would see, it would be a seaside resort. We'd be able to smell the salt in the air effectively, and we'd certainly be able to measure it in our ice core. But we actually found that it didn't change, and that implies that the ice shelf didn't retreat. So it's kind of good news and bad news. The bad news is that the ice sheet was smaller in the last interglacial, but the good news is we didn't lose that ice shelf, which is crucial for holding back the inland ice. So it means it's not quite as bad as some people have suggested it could have been.
Right. So that ice shelf acts almost as a barrier to stop the ice sheet from slipping into the water?
Exactly that. It acts as a restraint. We actually talk about it as restraining. You think of it as a hand pushing back against the ice and stopping
holding it in place.
Yeah, exactly.
Okay. Very interesting. Okay, super. Thank you very much, Eric, for explaining that to us. Does anyone have any observations or comments to make to Eric? Yes, Gael, what's your question?
Were you able to reconstruct the volume that were lost at the time from West Antarctica?
I would probably not claim that we were that precise. I mean, we could make an estimate for how much the ice where we are thinned, and we can look at ice sheet models that have been run for the last interglacial and see whether they're consistent with what we said, but we can't actually estimate it ourselves, I think, is the answer. So the main benefit of this is that it enables us to rule out certain versions of ice sheet models that either suggest the ice shelf disappeared or that suggest that nothing at all happened.
It gives you a more accurate picture of what was happening at that time.
Yes, but we need people to run more models in order to have more chances to understand what happened.
Well, we're going to come to that in a sec, I suspect. Excellent. Perfect. It's a wonderful segue. Alessio, would you like to ask something?
Yeah, I have a question for you, Eric. The last interglacial was long, like 15,000 years, more or less. Do you have any clue for when the melting happened, early, late, in this long period?
Well, I'm pretty sure, although we actually are missing a very small amount of ice right at the beginning of the interglacial, but it's pretty clear that it was at its minimum at the beginning of the interglacial, towards the beginning of the interglacial.
Okay.
So I think that's probably not surprising to us based on other things that we knew, but that turns out to be the case.
Confirmation.
Yeah.
Okay. Alessio, I'm going to turn to you now, actually. Warm Coasts offers insights into sea level and storm scenarios that can help us to assess the extent to which global temperature increase will impact our coastal areas. Eric's walked us through what ice core samples can tell us about the ice sheets in the last interglacial, but can you tell us why that period can help us with simulations for the future?
Well, yes, of course. Well, first of all, Warm Coast was born because I don't like to go on the ice as Eric and his colleagues do. I like to be more on tropical settings. And so this is where we are looking for proxies of what happened in Antarctica. How can it affect the coastlines even far away from Antarctica.
So, Alessio, can I ask you to explain what is a proxy?
Oh, yeah. A proxy is basically something that we can read in the geological record that gives us a clue about a property of what happened on our planet. We have proxies for sea level, for example, a coral which was growing back in time in an old reef, or we have proxies for storms like sands deposited on top of a coastline that were deposited in a certain way that remind us of storms.
So it's like evidence.
Yes, it's paleo evidence.
Paleo evidence, that's great, wonderful.
Paleo evidence for
past events.
Yeah.
Super. Okay, so tell us a little bit more. Sorry, yes. So tell me about why the last interglacial is so significant on this level.
Well, the last interglacial is very significant because this is the last time the Earth was, let's say, I don't want to say as warm as today, but slightly warmer than today. So we speak about, there are many different estimates, but we speak about a couple of degrees Celsius higher than pre-industrial globally, and the poles we think 5, 8 / somebody says a little bit more degrees warmer at the poles. So we are speaking about a world that is very similar to the one where we are, towards where we're going. So that's something interesting to see. If this happened in the past for different reasons than today, how can we try to project the future? How can we try to understand better the future by using the past, which is basically the foundation of geology, I would say.
Right, super. So what did the Warm Coast projects actually do? And then please tell me what you found. So what did you do?
So what we did was basically going in different sites along the Atlantic. So we started from Patagonia in Argentina, and we drove our way up all the way to Brazil, then to the Caribbean coastlines. Then we went into the east coast of the United States, looking for these proxies. So looking for ancient corals, ancient beach deposits deposited in the last interglacial, which could give us clues about what happened in terms of sea level and storms during this past period. So we wanted to have a picture of the Atlantic during this past period of time by looking at paleo corals, fossil shells, and cemented beach deposits in slightly above modern sea level. So this is what we did, and what we used was basically lots of techniques, such as other than normal field geology, we would have a ground penetrating radar to look under the surface to see how the beach was responding to past climates under the surface. And we used many different dating techniques, because whenever you find something like a shell or a coral which can be dated, you can use different geochemical methods to basically assign to it an age.
Yeah.
We don't know how old the shell is just by looking at it. We need to bring it in the lab and try to establish the age.
Sure. It sounds like you get together quite a lot of various disciplines here, because it sounds like a broad range of specializations that permit you to have these insights. Is that the case?
Yes, quite a lot. Actually, I'm a field geologist, so I was the one basically doing the measuring and collecting in the field. Yes. Yeah. But then, lots of colleagues come together, lots of different labs come together to actually adopt the different geochemical methods that you want to use to date a shell, for example, or a coral. And so you need to have lots of good collaborators scattered around the world and, work with them.
It also sounds like you managed to generate a huge amount of data. You were looking at so many different things over such a large geographical area. So how can people have a look at your data? Is it just for other scientists, or can anybody interested have a look? Tell us a little bit about how that is accessible.
Well, actually, that's interesting, because it's absolutely available to everybody. We have a website where we collected not only what we did, what we found around the world, but what people like us found from 1930s up to today. So we have about 1 century of research summarized in a big database, which is called the World Atlas of Last Interglacial Shorelines. Where basically anybody can go and look and see if they have maybe a paleo shoreline, on their backyard.
Yeah, fascinating.
Which is often the case because there are several thousands of these places scattered around the globe.
Yeah, you might find yourself near one. And what's the website, please?
It's www.warmcoasts.org, and then you navigate to Wallis.
Wonderful. Navigate to Wallis. That's what we should all be doing. Well, I'm not far away from Brighton coast and the white cliffs of Dover and that area. So, maybe there's something there. There's lots of interesting fossils on the beaches around there. So maybe there's some other stuff.
They're a bit older, but you might find something there from the last glacier.
Yeah, that's true. It is older. I've just remembered my little tiny bit of geological knowledge.
Yeah.
Nonetheless, have a look and see if your area actually has some information for you. So finally, is there something that you want us to remember from your project? Is there something that you think is of particular interest maybe to anybody charged with making policy, or any takeaways?
Well, starting also from Eric's research, so we know that Antarctica is probably going to be one of the issues that we have to face in the future, right? And we are probably already half facing it. And what we found was that compared to what was done previously, it was thought that sea level during this period, during the last interglacial, was, say, 5 to 10 meters above present. But we start, also thanks to our research, we start to think that it was about maybe a bit lower than that, like 2, 3 meters, 4 meters maximum as a peak during the last interglacial. Now, different ice sheets could have contributed in different ways or with different timings, hence my question to Eric before. But it's actually very important to remember if in a warmer period, similar to where we are going, like 2 degrees Celsius global is in the talks, right? Is in what we are talking about in terms of policy. So if this is what was produced during a warmer period, let's say a couple of meters of sea level rise, then think about our coastlines. And even a meter of sea level rise, it's quite a big problem for us. So we need to think about it.
Yeah.
And I live in Venice, so...
Yeah, some places more vulnerable than others.
Yeah.
Yeah. Thank you so much, Alessio. Does anyone have any observations or questions for Alessio? Gael, yes, please.
And what about the storms? Did these change anything with time during that period?
Well, I can tell you that finding the proxies for the storms was incredibly difficult. We tried hard, like super hard. So I can't give you an answer because we found some evidence of past storms, but we could get to the point where we refined the models that we borrowed from coastal engineering, basically, to understand more about the storms. So this is a question we're leaving for the future generations of scientists. There are, I think, places where you can see, like in the Bahamas, in some places, you can see that storms were possibly a bit stronger than today. And one of the things I am more convinced about from some proxies is that probably there was a change in direction of the storm, not as much in intensity, but in direction. I mean, if you think about the fact that today, everything we built on the coastline is based on intensity and direction of a storm, like a harbor construction is based on intensity and direction. Changing direction, even just a few degrees, it's actually something very, very dangerous if it happens. And in some places, we think it may have happened in Argentina, for example. So there's something to be aware of.
Something else to add to the picture.
Yeah.
Yeah. Thanks for that question, Gael. Gael, I'm going to turn to you now. We need a better understanding of the interactions between the atmosphere, the ocean, and the ice sheets, which is where the PROTECT project comes in. So, Gael, can you tell me, why did this field of research attract you?
Actually, I started my research by studying past climate. And actually, during my PhD, I worked together with Eric on the EPICA project on the Dome Sea ice core in Antarctica, which turned to reveal the history of climate for the last 800,000 years. And it was some 20 years ago. And at that time, new satellite observations started to reveal that the ice sheets were losing mass and contributing to sea level rise at a rate higher to what we were expecting. So that was typically for a young researcher an exciting topic. And also, sea level rise is not simply a scientific topic. It is a fundamental issue for the long-term organization of human societies. So we already know that sea level is rising. We know this process will continue for centuries. but at which rate this remains a key question even after 2 decades of efforts by the research community. So having a modest role in such a big societal question was really appealing to me. And from a scientific perspective, what I personally find fascinating is the highly nonlinear behavior of ice sheets.
So the highly nonlinear behavior. So what do you mean by that when you say nonlinear? You mean it's not predictable? Just because something happens at one point doesn't mean it'll repeat?
I'm not saying that it's not predictable. I'm saying that the response is not only gradual in a simple and predictable in a simple way. There are thresholds that may exist and beyond which part of entire region of the ice sheet could undergo a self-sustained retreat.
Okay. Yes, I see what you mean. You mean that there are triggers that can make things happen in stops and starts.
Exactly.
Yeah. Okay. Can you tell me then, PROTECT brought together these various parameters, that the atmosphere, the ocean, and the ice sheet. So, we've talked a bit about the ice and what that can reveal, and also, what studying the coasts now can tell us about the past. You kind of brought all 3 of these things together. So can you tell me a little bit about what PROTECT project actually did?
So the largest uncertainty in the coming sea level rise for the coming century is clearly attached to the evolution of both ice sheets. And the only available tool to investigate the future, similarly to weather forecast, actually, it's numerical models. So PROTECT aims at contributing to improve ice sheet and climate models and hopefully better constrain the uncertainty in future sea level rise. And there are various ways to do so. First, we need to better understand some critical processes and their representation in the numerical models. So, for example, the water from the ocean could flow below the ice sheet, lubricate the bedrock, and enhance the sliding of the glacier, increasing its flow toward the sea, and then its contribution to sea level. Second, even if ice sheets are far away from us, the ice sheets are not isolated from the rest of the climate system. They respond to the forcing of the ocean, of the atmosphere, even the Earth crust and mantle. So better representing this interaction in the models is key. It's basically a reminder of an artifact of the past. Today, Scandinavia is rising up because some 20,000 years ago, there was a huge ice sheet. So due to the load of the ice sheet, the Earth crust sink, and now there is no more ice sheet, so it's going up. And it's also the case in Greenland and Antarctica because the ice sheet were bigger before. And if we continue losing mass, this rise will change. So we have to take into account this change in this.
So the notion is there that the land might rise slightly.
Exactly.
Oh, okay. So that's an intriguing one. Okay. So we might bob up a little bit more like a cork above the rising levels. So movements in the ice and the dissolving of the sea ice raising the levels of the oceans, but also perhaps causing land masses to rise slightly.
Yes, typically in Scandinavia, today the sea level is not rising. It's dropping. And actually the sea level is not dropping. It's that locally the Earth is rising up.
Oh, it's fascinating. Thank you. Any other kind of examples of things that you have to take into account when you're doing your modeling, characteristics?
Yes. Typically, Antarctica is extremely cold, and the melt at the surface of the ice sheet is extremely limited. But depending on the climate evolution, it might really change into the future. And we know from Greenland observation that some melt leads to more melt. It's what we call the positive feedback loop, and it's important to take into account. Also, we know that in Antarctica, the change we are observing are due to intrusion of warm water from the ocean below the ice shelf that fragilize this ice shelf and lead the grounded ice sheet to flow faster. So we also need to better understand this connection between the ocean and the ice sheet.
After all this work on modeling and these complex modeling systems that you've managed to create, can you tell us anything from the project that really stands out in your mind as memorable or something that we should all really take note of?
I think there are 2 major things that are emerging. The first one is that we often hear that ice sheet models are disagreeing. I think they are agreeing much more than what we think for the coming decades, and that the amplitude of the sea level rise for the coming decades can be narrowed down. The other point, and I think this is really important, is that because of this threshold, we have And because the ice sheet and glacier are relatively slow element of the climate system, we have what we call committed sea level rise. So today, we have already launched a given amount of sea level rise. Typically, if we look at the glaciers, whatever we do, even if we follow the Paris Agreement, we likely on the long term have lost 30% of the glaciers. But depending on what we will do in the future, we will commit even more on the long term.
Right. So it's a long-term projection and we're committed, as you say, already to a certain amount. Thank you. That's very interesting, Gael. Thank you very much. Does anyone have any questions or observations to make? Yeah, Eric.
Gael, I mean, you're obviously looking at both the Greenland and Antarctic ice sheet, or I think you are. So what can you tell us about which of them we should be most worried about?
I would say that it's Antarctica. It's Antarctica for two reasons. It's first because it's absolutely huge. It's 60 meter, approximately 58 meters of sea level that is over the continent of Antarctica. When Greenland, it's about 7 meters. So in terms of potential, there is much more ice that can be mobilized to go towards the ocean. And also, it might be much faster in the contribution to sea level rise if we have this instability starting popping up and rising up in the coming decades and centuries. So I would fear more on Antarctica, but I'm biased. That's the ice sheet I have in my heart.
It is a very compelling area. I remember reading a book many, many years ago and always being totally caught up with the notion of Antarctica now. It's a. Have you been, Gael? Have you visited?
Yes. I was in Domsey in Concordia some 20, almost 5 years ago.
Yeah.
That was great. And you realize how big it is.
Like a completely different alien environment. Yeah, fascinating. Any other comments at all or observations to make?
Well, I was also going to ask Gael because he's much nearer to sort of application and policy than Alessio and I are. So do you feel that people are listening when you warn them about sea level rise?
This is a very hard question. I would say yes, they are frightened, but they don't listen that much. In the sense that we are, and sea level practitioners are most interested in the coming decades, when I think that the issue is on a longer time scale in our global organization. And I think this is hard to explain that, yes, what we are doing now is impacting generations of people and that we should act now.
Well, that's a strong way to end the episode. Thank you very much. Excellent. Okay. Thank you for your important work, guys. And at least it's reaching a slightly wider audience now. Hopefully people listening will take it on board. Thanks for your time.
Thank you.
Bye.
Thanks a lot. Bye.
Bye-bye.
Goodbye. Thanks for coming. If you've enjoyed this podcast, follow us on Spotify or Apple and check out the podcast homepage on the Cordis website. Subscribe to make sure the hottest results in EU-funded research and innovation aren't passing you by. And if you're enjoying listening, why not spread the word? We've talked about how robots can help small wine producers stay in business, innovative ways of identifying the chemical agents used in possible terrorist attacks, and how the gut microbiome might impact the way patients respond to chemotherapy. Maybe you're involved in a project or would like to apply for funding. Take a look at the Cordis website and see what others are doing in your domain. So come and check out the research that's revealing what makes our world tick. We're always happy to hear from you. Drop us a line. editorial@cordis.europa.eu. Until next time.